Okay, when atoms get close together, valence electrons interact. Basically, you create a lower energy or more stable molecule. That's a bond. That's all it is the valence electrons reacting. That's why we talk about valence electrons all the time. Okay, so lower energy bond, get a new compound. Everything wants to be a noble gas because those are stable, so that's why they take electrons or they share electrons. Okay, two types of bonding. Intramolecular, which is within the molecule. This is the type of bonding that when I say a bond, that's usually what we're talking about, right? When I say a chemical bond, we're talking about the intramolecular bonding, right? Within the molecule that makes the molecule up. Okay? That's the most common thing that we say. Inter is between the molecules, different molecules. Between the different molecules. And the intra are much stronger. Okay? So the ones that hold the molecule together are always going to be stronger than the ones that are different molecules interacting with each other. I won't say always because there's probably some exception out there, but most of the time. Okay, intra. So you know these three, well, you know the general types. We're going to break them down a little more. So we have an ionic bond. And then we said, in the past, we would just say ionic, covalent, right? Ionic is metal, non-metal. That's what we said. I don't really want to write that. That's like the simplified version, right? Something on the left side of the periodic. This is when I need a periodic table up here. Something on the left side of the periodic table and something on the right side. So something like calcium and fluorine, a metal and a non-metal, is generally an ionic bond. Whereas if you have two non-metals, like sulfur and oxygen, we would have called that a covalent bond. But you can break covalent bonds into a couple of different types. There's non-polar, covalent, and there's polar covalent. Polar means there's essentially a charge. Okay? Polar covalent have a charge separation. Due to electronegativities. Non-polar is it's a very tiny charge or you don't have any charge at all. But we'll talk about that right now. Okay. So, electronegativity is a measure of the atom's ability to attract electrons. And we use the symbol En. E capital N, I guess, is what they technically should put. And the difference in electronegativities will tell you what type of bond is taking place. So the simple illustration is an ionic bond. You get one atom takes the electron from the other. All right? You're not sharing. And then in the past, you would say a covalent bond is the sharing of electrons. But there's two types of sharing. There's equal sharing and there's non-equal sharing or unequal sharing. Equal sharing is non-polar. This is equal sharing. So they're pulling equally. The electronegativities are very similar. A polar covalent is unequal sharing, but not a complete transfer. Okay, so this would be like, I don't know, did he give an example yesterday? Did he? What was his example? Was it hydrogen chloride? HCl? Sodium chloride? Sodium chloride's ionic. Okay. I don't like sodium chloride because that's more ionic. Let's use HCl because that's the one up there. HCl. Which is more which is more electronegative? Chlorine. Chlorine's gonna pull electron density. So the electron density would be closer to chlorine than it would be to hydrogen. Even that's not a great example. Doesn't matter. All right. So polar covalent is unequal sharing. Right there, unequal sharing of electrons. So one is pulling the electron density more towards it. So you get a charge separation. All right. Ionic bonds. This is the transfer of electrons. So literally one electron goes to the other atom. When that happens, you get a positive charged atom and a negative charged atom. And the force of attraction between the positive and the negative charge is what on an ionic bond is. Did he have you pull out your electronegativity in your data table, in your data package? Okay. So there's numbers in your data package to calculate electronegativities, which we'll do. If the electronegativity difference is greater than 1.7, is that what he said? Okay. Then we would say it's ionic. All right. So if we're looking at sodium chloride, you're going to measure the electronegativity difference. Chlorine has an electronegativity of 3. Sorry. Sodium has the electronegativity of 3. Chlorine has the electronegativity of 0.9. So in your data package, is it the last page? Here it is. Did I mess it up again? Yeah, sorry. So sodium is 0.9. Chlorine is 3. That makes way more sense. So chlorine, sodium, get a calculated difference of 2.1, which is bigger than 1.7, is greater than 1.7. Therefore, we would say it's ionic. In the past, we would just say metal, non-metal, right? But now we can actually calculate these. All right. Because of this, it's an actual positive ion with a negative ion. And it's not just one sodium and one chlorine, it's a whole bunch of them. So then you get sodiums here and chlorines here and sodiums here and chlorines here. Then they have these attractions to all these other things. And ionic bonds essentially form a crystal network like this. This is what crystals are. One form of crystal anyway. Okay? As a result of them having all these interactions, they have high melting points. Because you're not just trying to break one bond, you're breaking all these bonds around it. Okay? Okay, so you get a crystal. They have high melting boiling points, right? Because you're breaking a lot of bonds. There are exceptions, okay? I wrote these notes in, so this part you don't have. So HF is covalent, not ionic. If you look at it's like 1.9, the difference. And this is like a scale, right? It's like not just distinct numbers. And I looked up other stuff on the internet, and they say If the difference is 2.0, then it's ionic. They consider it ionic. So this is like a cusp molecule. It also has to do with the size of hydrogen. BF3, if you look at that, it has a difference of 2.0, which looks like it should be ionic. Later on, we're going to look at the structure of these molecules. BF3 is like this. This is three-dimensional. So all these fluorines are pulling electron density away, and they're essentially canceling it out because they're pulling against each other. Cusp. It's just, what I mean is like it's close to the definition. We're saying the definition is 1.7 or bigger, right? This is 1.9, so we're close to that number. So it's like, is it ionic? Is it not ionic? Do you know what I mean? It's just close to that number. So the structure can determine if something's ionic or not. Like if you have the beryllium, the better one. If you have a molecule, it looks like this. Oh, carbon monoxide. Yeah, carbon dioxide, right? The oxygen wants to pull electron density away from the carbon, but because it's a flat molecule, they're pulling against each other, so there's no net difference in charge, even though you think there would be. Okay, so the structure can affect it. Later on in this chapter, we look at the structures of these atoms. Beryllium fluoride, I'm not going to ask you the reasons here, but this is the reason. Beryllium is really small, so when you pull the electron density off of it, or you essentially transfer the electron to fluorine, because it's so small, it's essentially just a bunch of protons sitting there. Its charge to size ratio is high, so it actually starts to pull the electrons back. Okay, so that's why it's more of a covalent. Even though the difference is 2.5, you think it'd be strongly ionic, but the electron density kind of gets, yeah, you'd have an what's the word? Like it would equal out in an equilibrium sort of dispersion that makes it more covalent than it does ionic. And then I just say, look, this is a sliding scale. It's not, if you're greater than 1.7, it's ionic. If you're less than 1.7, it is not. Okay? So, no, I'll make it very clear if it is or it isn't. All right. Okay, nonpolar. So, this is equal sharing of electrons. Can't write in overhead. All right. These are usually nonmetals. This is usually what we talked about when we said covalent molecules. Usually the same element. So the diatomics, so O2, Cl, the Brinkelhoff stuff. Okay? Because oxygen, O2, has the same electron density or electronegativity. Each is pulling in the same capacity against each other, so you get them to cancel out. So there's no net charge. Chlorine as well. They do have a range, though. It's 0.00 to 0.2. So if you have a small electronegativity difference, and oxygen's a double bond, not a triple bond, then you know it's going to be, we call that nonpolar. All right. They give the example of Cl2. Obviously, chlorine, the difference between the two of them is 0. So the electrons are spread equally. It has no charge in terms of this. Okay. The more interesting stuff is the polar stuff, in my opinion, which is the unequal sharing of electrons. Okay. So this is when the electronegativity difference is 0.2 to 1.7. So for example, if we have HCl, okay, the electronegativity difference is going to be 3.0 minus 2.1. There's the chlorine, there's the hydrogen, which gives us 0.9. Which is not 0 for equal sharing. It's not 1.7, so you don't get one electron ripped off, but you get a slight separation, okay? So remember we talked about electron density clouds and stuff like that last chapter? The chlorine pulls more of the electron density, and you get this partial. I showed you this last week, and I hope he did yesterday. You get a partial negative there and a partial positive charge because more electrons are closer to the chlorine than they are the hydrogen. This is called a dipole. And you can represent it with this sort of symbol. Plus charge, and that's the direction of the electrons. Okay? The arrow tells you where the electrons are going, essentially. Okay? So the electrons spend more time I'm putting time in quotes around the chlorine atom. Because remember, the electrons are moving, right? They're not just stationary. But it's not a complete transfer of electrons. That's why you get partial charges. And partial charges, as you can see, are that little symbol there. Okay, partial positive, partial negative. Can I flip the page? Give you one more minute. All right. We know we have trends in electronegativity. The highest electronegativity is fluorine. The lowest is francium. So basically the trend is like that, right? Going to the right and going up gives you higher electronegativity. Okay, so intramolecular bonding. Intramolecular bonding. I would say it's because these would have negative charges. You want to gain electrons. Whereas carbon can do both, and boron I would say give up. Sorry? Yeah, hydrogen can do both. It can gain or lose. We tend to think of it as losing, but it can gain one as well. All right. So, like I said, it's more of a scale. So this end is if these are electronegativities, ENs going this way. This end is 0. If there's no electronegativity difference, it's a non-polar covalent bond, no charge. You get equal sharing. All right. And you get 0 only if it's 2 of the same atoms. The transition comes at around 0.2, where then they would say you're shifting to more of a polar covalent. So one electron's pulling more electron density from the other electron. That's going to go all the way up to about 1.7 electronegativity. And then once you're higher up to 1.7, it completely rips the electron off, and you're into ionic bond territory. Okay? Like I said, I read another book that said this number was 2. We're going to use 1.7 anywhere, and it doesn't really matter unless you get really high charges. It's basically electron clouds are even, and then as you go this way, one of the atoms tends to pull the electron density until finally it just rips it completely off, and you get an ionic bond. Okay? Which would have the higher melting points here? Left or right? The right is going to have the higher melting points. So if you did melting points, melting and boiling points, melting point, boiling point is going, in general, increases going that way. Because as you get a charge separation, you get more interaction with other molecules. And that increases the boiling point and the melting point. That's why when you look at the halogens, this is a gas, this is a gas. Bromine's a liquid. Okay. Iodine is a liquid, and then well, you wouldn't see that one, but going down this way, because a bigger molecule has, we're going to learn it in a sec, has more electrons, you can get more sort of charge separation, which means you can get more interaction, which means you increase the boiling point or the melting point. All right. Did you guys do this? You did all of them? Some. All right, so calculate the electronegativity difference and determine the type of bond present. So you didn't do all of them. Why don't you finish the ones you haven't done? If you've done them all, that's awesome. I'm going to pause the video. I'm going to put up the answers, and then we'll see just to make sure. Is that okay?
Can I use your microwave and heat up so I can eat my lunch?
Yeah. What's that? Yeah.
How are we supposed to do it when there's more than two?
Just
do we
well, I'll talk about that one in a sec.
Do we just take one or just one of each?
Well, like, I don't know. Carbon's 2.5, hydrogen's 2.1. So you
there's
really just
4
have to,
hydrogens.
yeah, but you don't multiply it. So we haven't talked about the structure, so that's where this gets a little dicey.
Okay.
Um,
I think
this is the
CH4
structure.
isn't. Yeah.
Looks like this. So all the electron densities are going towards carbon, right? So you get a difference of 0.4. If it was the other way, they're all going to cancel each other out.
I mean, if it was the other way.
Like
Oh,
if it was like carbon on the out, or the less electronegative, more electronegatives on the outside, they would cancel each other out because they'd be pulling against each other. That makes sense. We haven't talked about that yet.
Oh, actually, here. Hold on. Also, yesterday, he was talking about that the differences between the solid, liquid, and why they do that. CH4 was saying how because the hydrogens are pushing on each other. That's why they form like that, or form that little square.
Yeah.
And also cause it to not bond.
Yeah.
Making it more difficult.
Well,
Why it's a gas.
we haven't looked at structures yet.
No.
So that's why it's not totally a fair question. So you just find the difference between the two. So like this one, beryllium.
But also Al2.
Just do aluminum and oxygen.
Are we just assuming, or not doing it without?
Yeah, don't worry about the numbers.
Structures. Okay,
Yeah.
And T
is T21 and AT 2.1.
AT is 2.2.
So it's a small difference. Yeah.
But it's gonna be. Well, the thing is, it's gonna be non-polar.
Yeah. Right.
Or well, it's also going to be non-polar because Te is.
They're both
is
gases.
smaller. Because that one is less than that, so that one's holding on.
Yeah, but there is such a small
there's a
difference,
structure.
right? It's all such a small difference.
Okay.
It doesn't make a big difference.
Okay.
All right, I'll talk about that right now.
Okay. Are we gonna dive into structures very much? Or?
If you want, but we're gonna do it. So. All right, people. There's the answers. Is that what we got? The first one, KF, is ionic. Excuse me. Second one, carbon monoxide, is polar covalent because it's 1.0. Bromine, Br2, it's the same atom. Same atom is always going to be 0. So that's nonpolar. Why is 1, sorry? Because it has an electronegativity difference greater than 1.7. So that's here. Its electronegativity difference is up here. If it's bigger than 1.7, it's an ionic bond. If it's between 0.2 and 1.7, it's polar covalent. If it's less than 0.2, it's nonpolar. Okay? So, okay, the methane one, I know the methane one's a little tricky. So if you just go carbon and hydrogen, you get 0.4, which fits into this polar covalent. That's what it is, all right? Later on in this unit, we look at the structures, okay? And the structures actually play a role in how electronegativities are dispersed. So we're not going to worry about that. Aluminum and oxygen, just find the difference. It's 2.0, so we call it ionic, which makes sense in the old school way because it would be a metal and a non-metal. And beryllium and AT, difference is 0.1, so it's non-polar. It's two gases, non-metals, sorry. Okay. Are we okay? All right. All right, so this is just what we just talked about, basically. If this is non-polar and this is ionic, you just get increasing polarity, basically, polarization. In other words, the electron cloud is equally shared, a little bit more here, even a little bit more to here, and then finally it just pulls the electron off, and that was what we call ionic. That's why these numbers are sort of guidelines. They're just kind of telling you how is the electron cloud distributed, essentially. All right. Did you guys do this table? Yeah? Did you finish the table? You're not supposed to do this one because we haven't done those yet.
Yeah, but we did everything else.
You did this?
Yeah.
And you got it all? Like you went over the answers and everything?
No.
Peoples?
I don't think everyone did it.
It was just
Okay. Well, I don't have the answers with me, so you're going to have to tell them to me. Who's done them? All right. So, okay. Sodium fluoride is ionic. What's the EN here? 3.1? Delta EN, I guess. Sorry. Methane, we just did that in the previous page. What is the methane one? What was it? 0.4, which fits with polar covalent. F2 is going to be 0, so nonpolar. Ammonium, or ammonia, sorry. 0.9. So that fits in nonpolar. All right. This is CCl4 is called carbon tetrachloride. That's an organic molecule. We're going to learn how to name organic molecules later on. What is the electronegativity difference of carbon tetrachloride? 0.5? If you're 0.5, you are polar. Polar covalent. All right. KCl is, what's the difference? 2.2, which means we're going to be ionic. SO3, sorry, 1, that's going to be polar. O2 is going to be 0, which is nonpolar. Tin sulfide, 0.7. Is that what I heard? 0.7, which is polar. I was going to write nonpolar. H2O, I can tell you it's going to be polar. What's the charge separation? 1.4? Bismuth chloride, 1.4? 1. Oh, 1.1. 1.1, which is polar. Calcium oxide, 2.5, which is going to be ionic. And magnesium chloride, which is 1.8, which would be ionic, but it's pretty close to being not. It's right on the cusp, right? So that's what I mean when I say cusp. I just mean like it's 1.8, and I'll put this back up in a sec. Where was the here? 1.7 was there. So 1.8 is like right here. So it's like, is it ionic? Is it polar? You know what I mean? It's really close to pulling the electron cloud away versus the big separation, but not fully separated. That's what I mean by cusp. All right. But under our data, you would just say it's ionic. Okay. All right. Now we're all caught up, right? Okay, let's do the new stuff. I'm going to pause the video there because or stop the video. I don't want to make an extra long video.